Very happy to have Max Xu, who will talk about arithmetic applications of random multiplicative functions.
Thank you for the introduction and thank you for having me. So today I will focus on arithmetic applications of something called random multiplicative functions. I think there have been at least 2 talks on random multiplicative function at IAS, one both given by R.M. Harper. One is during pandemic, so it's online, and another one is, I think it was on Peter's birthday conference, but he was also giving the talk online. But anyway, so instead of talking about the several main theorems about random multiplicative function, the proof, I will focus on number theoretical aspects, like how you can apply those techniques or theorems to get something maybe number theorists feel very excited about. Nevertheless, I will first start with, just in case you haven't heard about this, the object random multiplicative function is used to, we want to use it to model multiplicative functions. In particular, it's a good model for, let's say, pi m pi mod q, usually character mod q, or character like n to the it. And when you study the multiplicative function, usually you will go to study the corresponding L function. So zeta s and ls chi might be involved. And turns out RMF are good models to study some properties of this. And I particularly exclude Mobius function. I personally believe it's a very not a very good model for Mobius, but it would be a good model for typical character chi or for typical t n to the it would be a good model. So what is RMF? This is a kind of the motivation to study RMF. The definition is the following. For all prime p, Fp are ID random variables, and it's uniformly distributed on complex unit circles. So you define random variables on primes, index by primes, then you can, for general n, you define it in multiplicative way. You define Fn multiplicatively. Okay, that's the definition.
What is IIT? IID?
ID, sorry, it means like identical independent distributed random variable. So it's for each Fp is same distribution, and each distribution is like a uniform distribution on complex unit circle. And another I means independent. So it's like random variable F2 and F3 are independent. So on the primes they are independent. And then, but on the other integer index like Fn, we define to be multiplicatively. So F6 will be F2 times F3, so that F6 will depend on F2, of course, because of this.
So Fp itself is
independent. Yeah, that's the point. So on the primes,
is a number.
So it's a random variable indexed by p. It's a
on the unit circle.
Yeah, uniform distribution on complex unit circle. Okay, that's the definition. Now I directly jump to perhaps the first quite amazing result. Okay, I should mention maybe a little bit of history. So the original motivation people studied this were going back to Winterner, like 1940s. So his motivation was to trying to use the RMF to model Mobius. Although I kind of, I said at the beginning, it's not a really good model for Mobius. Sorry, who was that? Winterner? Winterner. 1940s, that's his paper on this. He tried to understand partial sum of Mobius function. So the first theorem is roughly 8 years ago. That's called Harper theorem. So let Fn be a RMF. Then Harper studied the expected size, first absolute moment, let's say, of Fn. So each of them is a kind of random variable with distributed on the compensation circle. Your first guess would be that you should compare this size with like the square root of x. But he proved that this actually quite surprising. It's a square root x divided by log x to a quarter up to a constant. And this confirms a conjecture of Harrison. Harrison conjecture is a lit over of square root x. So this is kind of like better than square root cancellation phenomenon. And I won't mention too much about the proof, but later I will indeed mention some key ideas in the proof in the later part of the talk. But maybe just to give 1 minute to appreciate the theorem. So if you naively say, if you use Cauchy-Schwarz, then the first moment you can bound it by.
Sorry, can I ask? I would have expected a log in the numerator because for Brownian motion, you have the law of iterated logs about the displacement. Yeah, but the multiplicativity is making that is what's responsible for that log being in the denominator instead, right?
You said you expect log or you didn't?
If it was instead of Fn being multiplicative, if it was just IID plus minus 1, so it's a Brownian motion.
Yeah.
For Brownian motion, you expect divergence like the variance, the distance from the origin at time x should be like root x log x.
Yeah, I know what you are talking about. You're talking more about almost surely the large values of. That's exactly true for independent case. That's like square root x maybe times square root log x. That's exactly you are correct in that case.
Multiplicativity.
But now here multiplication makes this actually better than square root cancellation. But that's also why when Harper theorem come out, it's big surprise because people, let's say Harrison's conjecture was proposed. It was a surprise why you expect this has even better than square root cancellation. Okay, if you use Cauchy-Schwarz, then this is bounded by the second moment. But now, because of our definition, these are RID for primes. Actually, there is a nice orthogonality, perfect orthogonality here. So basically, maybe I can write one more line here. You use that if for any Fn and Fm, if the n and m are not equal, the expectation basically 0. So it's exactly counting how many terms in your summation. So you get square root x trivially, and then this question is this theorem is saying you have better than square root x. Okay, this is a kind of depending on how you say. If you like it, if you don't like it, you can say this is not a number theoretical theorem because maybe you say everything is random. I want to get something deterministic. So then I focus on first application, which I call type 1 application. To prove anything about random function, then the first thing you want to try is that if I replace RMF by a deterministic or typical character, what happens? So it's type 1. That's 9th thing you want to try first. Replace F by I, or let's say HIT. Then what happens? Can you prove the same theorem? So that's a second result of Harper. I'm giving them for deterministic. So the theorem is following. Again, that F be an RMF. Sorry, what I'm talking about. Chi be a division character mod Q. Now you do the same thing. You can see the sum of chi n. You sum it from 1 up to x. And now here, instead of taking expectation over a random logic function f, you say I just consider the family of all chi mod q. And normalize by number of characters. That's q be prime. Okay, I can normalize by q minus 1 number of character you have. Okay, here's the relation. There are two parameters now. One is the summation up to x. Another one is the conductor q. So essentially the same result, exactly the same sieving. I will write more carefully. So it's log something called Lx plotted. And Lx is defined to be, let's say, the minimum of x and q over x. So there's some kind of duality here. But if you assume x is up to q to 0.49, then this is log x to a quarter. So exactly the same series. And the upper bound is known, lower bound is not known, but we believe this is sharp result. So this is what I call the kind of a type 1 application. You just try to see if you can prove kind of similar result for objects like a chi mod q. And similarly, the same theorem holds for n to the it. So instead of chi n, you can put n to the it here. Instead of summation, you put it integration. And the conductor q will change it to capital T, let's say. The same result, you can get exactly the same shape of saving. Okay, and maybe you're wondering how to prove this, and a simple one-line answer is like, kind of obvious, like you need to reduce this question to this random case. You need to de-randomize something, and then apply that theorem as a black box.
But could you sort of motivate for us why we would expect this little o square root x?
That's actually, I will mention the proof later, if that will make you happy.
But someone conjectured it before, so why did they conjecture it?
That's actually, I don't know, I probably Harrison was present to ask. And actually before Harper's result, Harper was one of the authors trying to disprove this. They proved lower bound square root x divided by log x, maybe to the 10th power, for example. So it's very close to disprove it, actually. This is related to, later I will talk about, is related to the critical chaos of Gaussian multitude chaos. I will mention this log as how it comes from. Okay, this is the first type of application. I will mention the second type of application of this result. So it's more like you want to, instead of your chi is not the object you are really interested in. You are more like use chi as a kind of a tool. So I don't know how to summarize, but I'll give you an example. Use chi as a second rule. And it's not really the object you really want to study. So I give you an example is the following. So okay, first, maybe I first mention Harper's another theorem, and I give you an application of that. So Harper noticed that the second theorem can be slightly generalized. So if we for all x up to conductor, let's say capital Q. Maybe, sorry, I still use Q. Then you can do the following thing. You can twist by chi n. You can twist chi n by some multitude function an. And then do the same thing, sum of chi. It's still like same kind of thing. So what is an's? An is some multitude function. So it's very crucial. It's an is a multiplicative. E.g., you can choose an to be Mobius function. And then, in fact, the object you really care maybe is an, and you want chi n to play some to play a second role to help you to study something. And one question he proposed, let's say Hubbard's conjecture. This condition actually is very strange. It shouldn't be there because after you twist by another multiplicative function, let's say mu n, you shouldn't care too much about the periodicity anymore. It's kind of destroyed here. So this condition is believed to be, you shouldn't be able to remove it. And if you can really remove this condition, let's say to prove a similar result for x for a much larger range, then you can have some nice application. So Hubbard's conjecture is x over q basically can be removed. It's still open. And an application of this is Mobius cancellation over short intervals, for example, or Mobius function over arithmetic progressions. I would write in short interval case, it's like easier to motivate. So if you write Mobius function over short interval, you care about something called Mobius cancellations, like if you wonder if this sum will be little o of y. And if you use the Perron's formula, roughly speaking, this one, by using complex analysis, you can write it as more or less you want to understand the average of this kind of integral. Okay, so it's kind of you want to understand integration of this and exactly
Offers conjecturing that for arbitrary A, arbitrary multiplicative A.
So
Modulus less than or equal to 1, what's it?
yeah, okay, good point. He didn't make that very precise, but here also, Peter mentioned good point. Maybe let's say it's bounded, let's say it's at most one or something.
But then it's a very strong, I mean, you can't state it then as a bilinear estimate. And it's an L1 norm, I guess.
Yeah, okay. So this theorem is proof for this version.
Yeah, yeah.
And then for conjecture, I guess he really had in mind probably Mobius.
Okay, then
Yeah, okay. Maybe I should say.
it's false if you put arbitrary A there. That's mine.
Yeah, okay. It has, okay, make his conjecture more likely to be true for AS. Equal to mu n, for example, of the wave function. Okay, if you use Perron, you basically, this looks like something like this. You care about mu n twist by n to the IT on constant times x, I guess, and dt. And this is exactly the expected in terms of character n to the IT of sum of mu n twist by. Okay, in that language, it's basically exactly this. If replace chi by integration. So I don't write it again. And if indeed Hubbard's theorem apply in this case, this will be up to square root x divided by log x, let's say to a quarter or something. And if you want this to be little of y, so that means if Hubbard's theorem holds in this case, then you only need y to be, say, bigger than this guy. So it's square root x divided by log x. Let's say a quarter plus that or minus that. So this breaks the square root barrier. It's saying that even you can choose y to be slightly smaller than square root x, you still have Mobius cancellation. The best, so if you assume RH, you can do something like x to the half plus epsilon. So you cannot go down below half. The best unconditional results due to Multiplicative-Hiary-Keating, they can prove x to, I think, 0.55. So this is really, if you can prove this result, you can go beyond to square root x. And now you want to check if Hubbard's theorem indeed satisfy this, is satisfied here. But if you look at it, you realize it's not. You need something like x go to the t square. So it's conductor square. But Hubbard's theorem can only go to x up to t, it's cube, like conductor, let's say. So that's the issue. We were interested in this, but I just give a quick comment maybe. So Victor, a former student of Peter, and I will prove theorem is saying that if you're assuming ratio conjecture, So it's a certain conjecture about how evaluate L function, ratio of L functions. If assuming that the ratio conjecture is true and plus IH, you can prove Hubbard's conjecture for this case. So maybe a small corner to.
Yeah, so, I mean, what you're saying is, was a short sum, doesn't depend on the zeros directly, that's why you get beat square root, yeah, over the family.
So ratios conjecture plus IH imply Hubbard. And as a consequence, you can break through that. Okay, this is the second type of application I want to mention. So it's like you may not really directly want to study chi, but chi is useful to to capture some arithmetic information maybe from the object you really care about. Then understanding this can also be helpful. And we believe Hubbard's conjecture should be true for Mobius case at least, but we don't know how to prove. But at least assuming ratios conjecture, it seems correct. Okay, that's the first two type of application. It's more like using the techniques of studying RMF as a black box. You don't need to understand them too well, but you just kind of plug in them and see if you can get some nice applications. The second type of application is more like a connection to another well-studied fraction in recent years, and because the proof techniques are very connected. So here is the place I will maybe also answer Akshay's question, where is log is coming from? So now we're going to some kind of level of details of the proof. So that's a third type of question application. So maybe the method of proof and how this method connect to other fractions in number theory. And the keywords here, the object we want to study, actually, now I can write down more, is a Gaussian multi-chaos, GMC. And versus log correlated field or log correlated structures. And Gaussian multi-chaos will be used in study RMF. And log correlated structures also kind of appear in RMF, but also appear in Riemann zeta function. And in particular, be very important to understand local maxima of Riemann zeta function on the critical line. So this is related to something called Fyodorov-Hiary-Keating conjecture I will mention in a minute. Let's see how I want to use the board. I just keep here. Maybe here's okay. So how to study this sum of Fn? Well, it's connected to by using complex analysis. It's not too hard to believe that you want to kind of to have some kind of random version of zeta function. So it's connected if you study the generation function. These objects will be very important in the study. And this one is really looks like zeta function. It has a nice random Euler product structure. Okay. To be more precise, it turns out, for example, in Hubbard's theorem, this is the first theorem, let's say. Roughly speaking, if you want to understand the, let's just say upper bound, one norm of this actually can be, okay, this is the put a small question mark. It's not that rigorous, but to give you a feeling what happens. So this will be like, you can put a square root x here, and then you will get something like, understand this kind of function. So it's so 1 log x times. I give it the name, maybe we call it FS, the random Euler product. So it's f plus it squared.
Okay, assume the random Euler product has a natural boundary on a half, right? So
Yeah.
what does it mean to put f for half plus it?
So later you'll see that it what do you mean by a half? Like
I forget, where does the natural boundary of this function? Is it a half? Is it
Why does
you
it-
push it a bit
to the left of a half?
yeah. And half will be the place we are studying.
I mean, it's not obvious that it converges beyond one. a
Yeah, but
priori,
it's-
but because of the
no, it's-
expectation.
Yeah, exactly.
Random guy.
That's it.
But where's is it zero? It's got a natural boundary where? What real part?
I think it's a real part bigger than 0, you are fine.
I'm thinking
It's
that's-
oscillating in the denominator.
Okay, so I hope you guys can look at this a bit careful. So what's this is? So this square root x exactly corresponding to the trivial upper bound at the very beginning, as I mentioned about if you use Cauchy-Schwarz, the L1 norm bounded by the L2 norm, so you get square root x. So the most difficult thing to understand is this expectation. So inside this expectation, first you have a square root. And then inside square root, you have this integration of this random Euler product. So naively, if you use Holder inequality, you put expectation inside. That expectation of the square of capital F, you still can compute it very easily. It turns out it's basically sum of 1 over p, I think p up to exponential sum of 1 over p up to x. So that gives exactly cancel this log x. So here, if you put expectation inside, again, it's similar as the Cauchy-Schwarz at the very beginning of my talk, which is useful. So you will not get better than square root cancellation. So you really need to study this structure. Now, what is this is? So this guy, if I write it as exponential, I can put it as a 2 times log of f. And then I'm doing integration from -1 to 1. And this log x is actually kind of the normalization, because if you take expectation of this, it's exactly cancel this. But anyway, I'll put log x here. This is more like the normalization. You want to understand this? Okay, so now here is a GMC coming in. So what is GMC? So roughly speaking, GMC is the following thing. The log of this capital F is basically like Gaussian.
I'm sorry, where is, other than in the denominator, where is x?
That's a good point. So I'm cheating a lot of this. So here, if you really add up to x, the Euler product really captures roughly p up to x.
So, okay.
So FS today is only.
Okay, now it makes sense.
Oh, okay. Good, thanks for your action. Okay, so you have expectation of this thing. And for each fixed t, this guy, okay, maybe I have a different color. So this log of f half plus it is basically like Gaussian. If you look at it, it's basically Gaussian because it's sum of fp over p to s. So this is approximately Gaussian, but not exactly, but let's say it's Gaussian. Let's say it's a Gaussian, I call it xt. Okay, at any given t, it looks like Gaussian. And now what you do is that you multiply by some parameter. This is some kind of parameter. And here the parameter is a constant 2. And then you take the exponential of this. After you take exponential, you are actually kind of doing summing or integration or summing, whatever you say, over all this kind of family of random variables. And you want to understand the distribution of this. And GMC is basically the definition. This is the definition of GMC with the parameter 2, let's say. Okay. I hope it's clear. It's a sum. It's basically this kind of a Gaussian. You take exponential with certain parameter, and then you sum it over this kind of Gaussian. And then you want to understand how large it is. That's a definite. That's a try to understand this GMC. Now going back to actually this question. So this parameter turns out can be very important. So here's the critical value. Critical value. So we replace 2 by a constant as lambda. Critical value is the following meaning. If lambda is very small, it's something called subcritical range, then you can always get a kind of non-trivial distribution. But if lambda is very large, then you probably get something called the supercritical case. Then you can get some basically degenerate distribution, like a 0 distribution. And when you have a critical case, then even you don't know. In general, you don't know too much about it. And it turns out in this case, 2 is exactly the critical value. So before Harper's paper, a couple of years right before his result, in probabilities or mathematical physics side, people realized in this critical range, you should further renormalize something. So the thing you further renormalize is roughly like e to the log of f squared. After you further renormalize this, basically mean you multiply this thing, you will get a non-trivial distribution. And if you compute this guy, it actually give you exactly log x. And going back to Harper's theorem, it kind of suggests if you believe RMF is indeed like GMC, it's kind of telling you that you should further multiply log x in order to get a non-trivial distribution to a certain power according. And then that's probably suggests the original sum should be little o of square root x. And this result from probability side actually kind of predict what kind of factor you are missing. Okay, so it's really kind of motivated first from here. Like probably give Harper intuition actually this conjecture is correct. And the proof method actually also boil down to how people find this. So okay, I'm talking about this GMC thing. I haven't talked about log correlated thing. And the reason why this is not easy to analyze is if you look at log f half plus it, let's just say call it xt, it's not id in terms of t. So for different t, xt and let's say xt1 and xt2, they are correlated. If you look at the expression, if t1 and t2 are very close to each other, it's kind of like a Riemann-Zeta function, of course. If the two t's are very close to each other, then they are correlated. But if you assume that t1 and t2 are kind of far away from each other, they are kind of independent. So that's like a feature of this thing. So it's not like summing over exponential of some ID random variables. That's the tricky part. And in terms of this correlation, people can understand the kind of precise write down the correlation. And the correlation is something called log correlated. And now I'm writing down this log correlated thing. In terms of it, I will just use a Riemann-Zeta function. So log correlated same for RMF or same for random Euler product, same for zeta function. Let's say if we have log zeta, if I uniformly at random choose t from let's say 0 to capital T, then you care about let's say log half plus it plus ih, that's h1. What's the covariance between these two? This function and log zeta half plus it, let's say plus ih2.
What are we varying?
The vary is little t. So when you choose little t, and then if look at 2.h1 and h2, and turns out their covariance is exactly what the called log correlated field is. Roughly speaking, this is like some constant. I think here is half, and log of more or less is 1 over the distance between H1 and H2. So if H1 and H2 are kind of very getting closer and closer and closer, of course, they are correlated stronger and stronger and stronger. But at some point, if they are same, then there's a kind of the boundary of this thing. So you take log of, I think here is the minimum, sorry. So the minimum of the two, one is this guy, another one is basically, they are the same. Another factor is log t. So forget about this part, it's basically telling you what is log correlating means. It just means log in terms of the distance. And this is structure, this covariance structure happens for log zeta and also for this log random zeta, of course. So that's kind of connect GMC study to log correlated field study. And the conjecture I mentioned earlier basically to study local maxima of log correlated field has a lot of common feature of study RMFs. So,
How's that related to Solberg's?
central limits here?
Yeah.
Okay, that's a good question. That's exactly what I plan to write down now. So Fyodorov-Hiary-Keating conjecture originally proposed probably in random matrix side, but let's only care about Riemann zeta case. So following conjecture, let T to be 0, capital T be chosen uniform at random. Then with high probability. So if you dislike probability, this basically is talking about the big measure. I'm speaking probability language, but it's same as it's just the big measure of the T. That you can study the log of zeta half plus IT plus IH and take a maximum of H up to 1. Let's say so you basically want on the critical line, if I random choose my small interval and each interval is like a constant size, I want to understand the local maximum on this small box when I random choose my interval like this. And going back to Peter's question, how people predict this, of course, use Selberg's the Selberg central limit theorem. So Selberg central limit theorem tells us that forget about IH. If I just random choose my T on this big box, then log of zeta is kind of distribution like Gaussian. Okay, that's at least
Log.
exactly. That's that's exactly the.
By the way, you know his joke. He said he didn't know it was a Gaussian.
He didn't know it's
That's
Gaussian.
right anyway, it's a Gaussian. He just,
Yeah, I think in the,
then I think he was teasing people and said, "Oh, that's a Gaussian." He was trying to-
okay. Anyway, that's a Gaussian and with variance standard deviation square root log. So that's the first information you have. The second information, of course, you know that the zeros roughly distribute like 1 over log T away from each other. So if you in the constant size, you kind of guess this might looks like log T number of independent random variable, and each one is a Gaussian. It's like GI with the variance Peter said. If this one is really look like this, then you can compute this directly if GI are independent. And then it turns out if GI are really independent, forget about all the dependency. This suggests this looks like log T minus a quarter triple log T. That's something, let's say we don't care. But it turns out the conjecture is slightly different. They realize this correlation will make a contribution in the second order term. So the mean time is still same, log T. And second order term turns out to be 3/4. That's a conjecture. And this 3/4 in some sense, if you like, there's a difference between the second order term is same as like why there's a strange log x a quarter appear in RMF case. So that's kind of similar philosophy. And I quickly mention the history of this. So there's at least three results I want to mention. I won't write down the name clearly. First, again, Polya, Bogart, Ratsville sound, we get the first order term. And then Upper, he got the and it's upper bound for the second order term. And now recent paper, again, is based subset of this. Again, Bogart, Roswell, they basically prove this whole conjecture. Okay, that's like the connection. I think I have 20 minutes, so I want to mention this anyway. This is again about statistics of Riemann zeta function. It's probably, I think it's, yeah, I want to give just a 2 minutes summary of one application we found about studying this local maximum of zeta. That was actually described in details in a talk given by Sam a couple of months ago. I still just want to mention the connection there again. So here's one application. Why we care about local maximum of L function. Application to Polya's problem. This is I think 1911, but that's the 1990s. So the question Polya wants to ask is how many quadratic characters ID okay, I use Peter's language to say positive definite. Okay, that's right, positive definite. So this definition you can find in a letter by Peter. I guess he did. Polya didn't state it this way, but
You surely knew what positive definite was, boy, did he know it.
yeah. Okay, so positive definite just mean like if you can see the sum of pi n from 1 up to x. So this quadratic character is basically real, and you want to understand if this is always non-negative for any x, then this is positive definite. And Polya basically wants to understand if I enumerate chi d by the conductor d, then how many of them are positive definite? And this was connected to zero zeros or whatever, but I just give a quick remark why this is connected to the question here. It turns out that in a theorem with Angelo and Sound, we can show this proportion is such a number is basically log digits in power, and numeric suggests this up to a constant c here. This is correct, and the really important thing for our proof is try to understand exactly local maxima instead of a Riemann zeta function, but we want to study. No.
You believe that there are that many, right?
Sorry?
You believe your upper bound is close to the truth.
Yeah, up to C. And we studied this. This is actually exactly perfect analog of log zeta. And when you choose chi d in a family, it's same as when you choose little t in a family. And this is small window we care about. And for us, we need to understand the local maximum of this. And it turns out, understanding this statistic will give you upper bound of this. So that's at least one arithmetic application. But why you care about this more like complex analysis statement about log zeta.
I forget, Sound had some numerics. Do you have numerics saying, because we don't know there are infinitely many with that.
Yeah, so the numerics induce that actually there are a lot, and we are not super confident what exactly C is. Originally, we conjecture C is a half by some random multifunction model actually, but numerics seems not exactly converge to half, so it's not clear. But at least it's
Power of log in numerics?
So, okay. We check this actually in another family, which is much more convincing. It's a kind of checking function field family. So log will become some other power, for this interesting question, actually the history was if you check how many of our positive definite, up to 73, they're all positive definite, and it's actually a quite large proportion. So it decreased very slow. We really believe it should be some log factor degree decay. Okay, that's the type 3 question. Now, what else we can do? I quickly remark about some recent development of RMF, which is most of them happened last month. I will list some of the results about what's a new development. And this development care more about the distribution instead of the size. So far, for example, Hubbard theorem and this determinant theorem about character sum, it's all just telling you the size. And now you wonder, if I know the size, what's the exact distribution? For example, if they're Gaussian. So this is more close recent development. So maybe it's not that arithmetic, it's more, some of them sounds more probabilistics developments. So we want to understand the distribution of some of some arithmetic trace, let's say. AFN. Really want to say for what kind of AN we can exactly determine the distribution now. So I just mentioned a couple of examples because there are so many of them. So maybe first example I want to mention is
So what is this? N up to X,
okay, sorry, yeah, always n up to x.
AN is bounded from
Yeah, AN is some whatever function you like. And now I want to say what maybe usually has arithmetic meaning. And then for this kind of twist, can you determine the distribution?
is A multiplicative?
That's one of the example I mentioned. So first, AN is an indicator of a polynomial image. What does that mean? So essentially, I'm just looking at sum of Fp for polynomial P. Actually, we can determine for all polynomial P. As long as it's not linear, this is Gaussian. Because linear is really a special case. And that gives you the Gaussian multiplicative chaos structure. In another word, GMC is very kind of, how to say, fragile. So you can kind of easily destroy it. So this is Gaussian. This is proved in a paper with Kluman, Stradov. This is roughly 2 years ago or 3 years ago. That's one example, and you can think of A as an indicator function, but it indicate a very sparse function. Okay, and also kind of funny because if you really determinist case, usually with polynomial phase it will be much harder, but in random case kind of opposite. With polynomial case, you destroy this GMC actually can be easier. The second type of example, before I talk about multiplicative, I talk about additive. So AN is additive. You can see that Fn is multiplicative, so I want to destroy it. So the coefficient we want to choose is, for example, if I choose an additive coefficient, then it probably destroy the multiplicative structure. E.g., let me choose AN equal to e to the 2 pi and theta. 2 pi I and 2 pi and theta. So what does that mean? So if you look at the sum of Fn and twist by e to the 2 pi and theta, and still normalized by 1 square root x, we show that this is also Gaussian. As long as theta is not close to rational. Of course, if you choose theta to be integers, then this is essentially Hubbard theorem. Then you should have better than square root cancellation. You shouldn't get Gaussian. You should get this basic tend to 0. So theta is not, we can quantify theta. For example, theta you can choose to square root 2. So for basically density 1 theta, it all satisfies what I call not close to 2. And it's very explicit. This is this joint work with sound. Okay, that's the additive thing. Now I talk about, so this is all like 2 years ago, 1 year ago. Now I talk about something 1 month ago. So this is some recent development by 2 groups of people. Now it's Peter's suggestion, AN is multiplicative. For example, the example I like here most is AN is an indicator function of sum of 2 squares. That can be covered, for example. if n can be written as sum of two squared. Now we know this is distribution. So this is a work by, first there's a random matrix version, first proved by probabilists like Najanudar and his co-authors. And then this number theory group by Fyodorov-Hiary-Keating and Modik Wang. The rapid proof following, if an has mean value theta, strictly lie in 0, 1. Okay, I didn't write this explicitly, but basically summing of an and look at its mean value. For example, sum of two squares will have mean value like when you write it as a multiple function, it gives you like mean value half. It's covered in this case regime. Then the interesting thing is that it's not Gaussian anymore. It's something like a Gaussian times a random virus that they call V infinity. Because V infinity is a random variable, but it's not constant. And it's positive almost surely. And it's independent. G and V infinity are independent. So at least it's a different distribution. The second distribution appeared that you will get Gaussian but twisted by something independent, but this is no longer a constant. And another interesting example also developed last month by Seth Hardy. So a key feature here, if you look at it, it's very crucial to not include 1 because this actually still kind of sparse set. So this is Seth Hardy, not that Hardy. So the graduate student of Harvard at Warwick. So it proves that if an is another multiple function, but its indicator function of n has a larger prime factor, has a prime factor bigger than square root x, let's say. So this is actually already positive density subset. And the interesting phenomenon he found here is that you shouldn't normalize by square root x anymore, because this already touched the GMC phenomena Hopper discovered. So you should really take into account this log x quarter feature. So here result is log x quarter divided by square root x. So you should enlarge the sum an fn. Actually, this will again Gaussian but traced by something, another V infinity, and similar thing like V infinity will be independent of G. Okay, this is so based on these two results, I personally I would conjecture if you just put a and b 1, the answer should be Gaussian traced by something, won't be Gaussian. So in the original theorem of Hopper, if you really ask about what's the distribution, then my guess would be the distribution is non-Gaussian, although it's not proved. It's very crucial that in Hardy's paper, you need this larger prime factor. Although it touches the positive proportion, but its multiplicative property is very crucial. Okay. Now in the final 4-5 minutes, I mentioned the final example that we have been working for a long time. Now we finally understand all the short interval case. So short interval case is proved out. So basically we study sum of fn and y is always little of x. In the short interval, for any integer n1 and 2, they are not multiple of each other. So you might believe the dependency is weaker. So especially when y is very small compared to x, you might believe Gaussian. But when y is like x, by what I said, what I conjecture or Hopper theorem, you believe they shouldn't be Gaussian. So it's not clear what's the truth. But now we finally fully understand this. So the first result along this line is Chatterjee and Sound. This is like 15 years ago. We can prove that as long as y is power of log away from x, then Gaussian. And then maybe 2 years or 3 years ago, we pushed this exponent to another more arithmetic meaning constant. If you can see the meaning for this constant, and you can, but I have no time to explain. So 2 log 2 minus 1. It's also Gaussian. And finally, this is still work in progress. So Harper sound. We can show that exists a deterministic factor, a scaling factor Vxy, such that the following is always Gaussian. X to x plus y, and you normalize by square root of Vxy. You always get Gaussian. But the Vxy depends on relation between x and y. So maybe I write in here. That's the important part. So when y is very small compared to x, of course, you just normalize by square root y. You can get Gaussian by the previous result. So Vxy turns out, roughly speaking, it's on order like minimum of y. But if y is very close to x, you should do something like Hardy did, or you just use a Harvard theorem. You should renormalize by multiplying a log x factor. So it turns out the threshold is around this. You compare log of x and y, and square root of this still y times log of x or y and log of x. And you also get Gaussian. So this is a transition range between x and y. Like how large is y is compared to x, you should multiply by this. This GMC structure will appear. If y is not large enough, then you should have this. I should mention a result by Cage. He also finds this kind of transition, but he only cares about the size. See also Cage results. And I didn't mention anything about the proof about the recent development, but anything if you didn't see log x factor, I would call it a soft method. You're using something called the martingale central limit theorem. So it's more like you don't study the subtle points about subtle thing about the GMC. But if you see the everything like this, V infinity appear or log x factor appear, you need to really work on details of this log correlated structure or GMC. Okay, I think I'll stop here. Thank you. Any questions?
In your RMF model, you're on the unit circles. Can you kind of reduce the randomness maybe plus minus 1?
Yeah, that's a good point. That's like something called Rademacher case. This is called Steinhaus case. I didn't mention that today. Yeah. So yeah, for example, for Harper's theorem and most of the theorem I put down here, Fn if it's a uniform distribution on 1 minus 1, the half probability results are same.
Prefer to do it because it's
I prefer to do this way because originally Winterner, he proposed a model, he proposed a Rademacher. He not only proposed plus minus 1, he proposed square free. So he only defined a square free integer because he cares about Mobius. He wanted it to be like Mobius. But as I said, I don't think it's a good model for Mobius. So I think in general, this Steinhaus model seems has more applications, and usually from technical aspects, slightly easier than this Rademacher case. But that's a good point. Yeah, there's all this model also studied in the literature.
and also in the probabilistic side of things, people try to reduce randomness by looking at things that are not IID, but maybe any four of them are independent, not fully independent, for example. Is there anything like this here that you do?
I mean, like a
Just
generalized.
try to reduce the amount of randomness that you feed into the problem.
That's a good point. So in the proof techniques, I skip a lot. Even in the first step, I said something like sum of f are reduced to the random Euler product. That's already use something called conditioning argument.
Yeah.
So you need to condition on maybe a certain number of small primes, and then use the rest kind of ID. That's how you play the game. For example, the condition argument used a lot of places, but I just completely ignore it today. That's the kind of same philosophy you said. Yeah.
Have you developed this for GL2s? So that I think it's not Euler product completely multiplicative, but multiplies according to a Hecker polynomial.
Yeah, exactly. That's a very good question.
No, because then it could have applications to the zeros. So you take an elliptic curve and you ask, and it's got a large conductor, it will have n zeros, the genus or whatever. But there may be a lot of zeros, logarithm number, on the y-axis, because that's your sum smooth with e minus ny. And if you take a mass form, it's even more interesting, because then it will be related to the nodal domains. So that's one of the reasons I was so interested in whether you could have no zeros, which you're saying on the y-axis, because that's a positive definite condition.
I see.
So you were surprising me by saying that you expect that a lot of them were the characters. I wonder if you introduce a more complicated Euler factorization, which is not linear, but quadratic.
Yeah, okay. That's a very good question. I plan to do, and I also know people are interested.
What the random such guy gives.
Yeah, and then also for that one, you maybe so the random model will be more complicated because sometimes you need to take care of the Hacker related.
Right.
Like why makes it more challenging. Yeah, but that's a good motivation.
You're using the Euler product.
Yeah, but he's assuming that it's completely multiplicative.
Yeah. For the sum model, Peter suggests you need to take care of the Hacker relation.
You just do 1 plus AP over P to the S, 1 minus AP over P to the S, plus 1 over P to the 2S.
But the question is how much it comes on
Yeah.
the square root behavior and the log. Maybe there'll be something that gets
Interesting.
more interesting.
Yeah.
Because there the zeros make sense.
Yeah.
Great sense.
Yeah.
In other words, people have worried about whether zeros of a modular parameterization or even of the derivative, where the derivative vanishes. Those are points where the modular map is critical.
Yeah, that's a good point. That's also okay. That's maybe connected one reason I dislike it. Plus minus one. Is it still recording? The plus one minus one model, because in Mobius function you have more structures like zeros. Like you connect to one with zero. You have functional equation and you connect to zeros. But if in this RMF model you completely forget about it's zero contribution. So I don't think it's a good model for Mobius.
I agree with that.
Yeah, it starts with a kind of.
I agree.
It starts with yeah.
I mean, you didn't highlight one thing in Hopper's work, and that was that you sort of ran them up to square root of the conductor, and then after square root of conductor, the functional equation, or the approximate functional equation puts you back to less than the square root. When it goes up to q, right?
Yeah.
You must use that.
Yeah.
Any more questions? No, let's thank Max again.